This video is going to be on the pH scale and buffers. So the pH scale tells us the acidity of a solution, and the values range from 0 to 14, and those are representing the H3O plus concentration, and that's why it's pH, the capital H. So if we look at some different substances, we can see that things like gastric juice, lemon juice, pop, orange, we've got milk, those things are going to be acidic. So if their scale goes from 0 to 14, at 7 is going to be neutral. Anything from 0 to 7 is our acid, and anything from 8 to 14 are going to be considered our bases. So these things would all be acidic. The things that are toward the bottom, like ammonia, milk of magnesia, drain cleaner, those are going to be bases. All right, so if it's an acidic solution, we said that the pH was less than 7. If it's neutral, it's around 7. And if it's basic, it's greater than 7. That also means that the H3O plus is greater than the 1 times 10 to the negative 7. We know if it's neutral, the H3O plus is equal to the OH minus, and it's 1 times 10 to the negative 7. And if it's a base, that means that the H3O plus concentration is less than 1 times 10 to the negative 7 because there's more OH. And there are different ways that we can measure pH. We can use a pH meter, we could use pH paper, or we could use indicators that would change color. And you can see there's some purple cabbage down here. So cabbage, there's also some flowers. Depending on the acidity of the soil, the petals on the flower will be different colors, but we can use those petals as indicators to tell if it's acidic or basic. All right, so here they just want us to find these things if they're acidic, basic, or neutral. So the first, if you would like to pause, you can pause your video and then you can come back. So if we have HCl with a pH of 1.5, that's less than 7, so that's going to be acidic. If we have pancreatic fluid with an H3O plus of 1 times 10 to the negative 8th, that means that's less than the 1 times 10 to the negative 7th. So that means it's going to be basic. If we have a soft drink with a pH of 3, that's less than 7, so that's going to be acidic. If we have a pH of 7, then that's neutral. If our OH minus is 3 times 10 to the negative 10th, that is smaller than 1 times 10 to the negative 7th. So that means the H3O plus is greater, making it acidic. And if my H3O plus is 5 times 10 to the negative 12th, that is smaller than 1 times 10 to the negative 7th. So that means it's going to be basic. Now when we calculate pH, it is a log function. So you're going to do negative log of the H3O plus concentration. And log is just a function on your calculator. You should have a log button. And typically it depends on your calculator, but on mine I push log and then my concentration. You may have to enter your concentration and then push log. When you do that, you'll get a negative number. So this negative in front is telling you just to ignore that negative and make it always a positive. So do log of the concentration, and then it should be a positive number if you ignore the negative part. All right, so our example says find the pH of a solution if the H3O plus is 1 times 10 to the negative 4. So you're going to push log of this number, and like I said, depending on your calculator, you may have to enter that number and then log. And when you do that, you get a negative 4. So the negative and negative cancel, and you get a pH of 4. Now, when we talk about significant figures for pH, the number of decimal places in the pH has to be equal to the number of significant figures in the number. So, for example, here we have 1 times 10 to the negative 4th. So this has 1. So that's 1 sig fig, which means I'd have 1 for my decimal place, 1 number. Here, 8.0 has 2 sig figs, so I would have 2 decimal places for my pH. Here, 2 in my number, therefore 2 decimal places. All right, so this one says find the pH of a solution with an H3O plus of 1.7 times 10 negative third. So if I do negative log of 1.7 times 10 negative third, I get a number that's like 2.77 blah, blah, blah. 1.7 has 2 significant figures, therefore I need 2 decimal places. All right, these ones we're going to find we have to find the concentration, or we're given the concentration, we have to find the pH. So if the H3O plus is 1 times 10 to the negative fifth, if I want to find the pH, I'm going to do negative log of 1 times 10 to the negative fifth. All right, and mine tells me that my pH is 5. This has 1 number, so therefore I get 1 decimal place. So my pH would be 5.0. Okay, this one says the OH minus is 1 times 10 to the negative third. What's the pH? Well, in order to find the pH, I have to have the H plus, but they're giving me my OH minus. So I have to do like I did on the first video, which was H3O plus times the OH minus concentration gets me 1 times 10 to the negative 14th. So in order for me to find my H3O plus, I'm going to have to take 1 times 10 to the negative 14th divided by 1 times 10 to the negative third. And this would actually be 1.0 times 10 to the negative 11th. So now I can find pH. I'll do negative log of 1.0 times 10 to the negative 11th. All right, and I had 1.0 has 2 numbers, so I need 2 decimal places. So we could say our pH is 11.00. Okay, this one wants me to calculate the H3O plus if I have a pH of 8.25. So we're going to go backwards. So if we're going backwards, I'm going to take 10 to the negative pH in order to find my H3O plus. So that means for 8.25, I'm going to do 10 to the negative 8.25. And on your calculator, you probably have a 10 to the caret button. So you're going to do 10 to the caret negative 8.25. Okay, when you do that, so I'll do that on my calculator. I got a number which is 5.6234113, and it goes on to the negative 9th. But since 8.25 has 2 decimal places, that means I need 2 significant figures. So I call it 5.6 times 10 to the negative 9th. Okay, this one wants me to find the H3O plus if my pH is 11.2. So to find my H3O plus, I'm going to do 10 to the negative 11.2. And I got 6.309577 times 10 to the negative 12th. And since I have 1 decimal place, I get 1 sig fig. So 6 times 10 to the negative 12th molar. So that means it's going to be answer A. All right, right, so there's 3 different reactions that we're going to take a look at. The first one is an acid with a metal. So acids will react with metals to produce hydrogen gas. So in this case, I have these acid. This is nitric acid. I'm going to react it with potassium or magnesium. Both those are metals. So I'm going to produce a metal salt because this is ionic. So a salt is an ionic compound. So what happens is this is a single replacement reaction. So the K is going to come in here and replace the H. So then I'm going to have K plus with NO3 minus, and those add up to 0, so it's KNO3. And then I'm going to form hydrogen gas, and hydrogen gas is H2 because it's diatomic. And it's always a gas. This, I could look at my solubility rules and find that it is soluble. And then we would balance my equation. Now in this one, Mg replaces the H. So I'm going to have Mg, which is a 2 plus, with NO3, which is a minus. So those crisscross, which is how I got the MgNO3 and then make hydrogen gas. And this is soluble because I could look at my solubility rules. Okay, our other one is an acid with a carbonate. So an acid with a carbonate, and a carbonate is always CO3, that polyatomic ion carbonate. So an acid with a carbonate makes carbon dioxide, which is a gas, makes water, which is a liquid, and then a salt. And this is going to be fairly easy to do because we know we are going to form carbon dioxide. So that means you're going to take and get rid of the C and the O. So you get rid of the CO3 term. And then you know you're making water. So that's going to get rid of that H and that other O here, since this was 3, H2O. So it means the pieces that are left, the Ca with the Cl minus, so we have Ca plus 2, Cl minus, those would crisscross, would make my salt. And then I could look on my solubility rules to determine that that was aqueous. This is going to work the same way. I'm going to get rid of those H's and those CO3s because I make CO2 and H2O. Then the pieces that are left, Na with Cl, that's going to make my salt. And then I would bounce my equation. Okay, the neutralization is the third reaction, and that's an acid with a base. And we always make water, H2O, and a salt. And there is a separate video just on neutralization reactions. Okay, the last topic of this video is going to be on buffers. And a buffer is a solution that maintains its pH even when I add acid or base to it. And in the body, we have different processes that occur in our body, and we have buffer systems that help keep the pH of our body fluids about the same. So for example, it said blood contains buffers that keep the pH of about 7.4. And if I get that pH too out of whack, that's going to disrupt oxygen absorption and some of our metabolic processes. So if we just had water and we added an acid or a base, the pH is going to change dramatically. So in this case, if I have something that's just plain water, we had a pH of 7. If I add some acid, the pH went down to 4. If I added a base, the pH went to 10.5. But when I have a buffer, it's going to level out that pH. So if I had a pH of 7 for my buffer, now a buffer doesn't have to be a pH of 7. That buffer could be any pH it is. It could be 4, it could be 8.7, whatever it is. But whatever the buffer pH is, it's going to keep it the same. So even when I add some acid, it only dropped to 6.9. And when I added some base, it only rose to 7.1. So it keeps the pH level. Now it does that because a buffer contains 2 parts. It has an acid part and a base part. And it turns out those are acid conjugate base pairs that we talked about earlier. So it has an acid part and a base part. So it can be a weak acid with its conjugate base, or it can be a weak base with its conjugate acid. But it's got to have both parts, acid and base, because that way, if you add some base, the acid part will neutralize that base that you added to keep the pH the same. All right, so it says, which of the following combinations produce a buffer? And then it says, do they or not, explain. Okay, so I look at the first one. I have HCl. That's one of the strong acids that I memorized, so I know this can't be a buffer because I have to have a weak acid or a weak base. So not that one. H2CO3, that's a weak acid. And over here, I have HCO3, which is its conjugate base. So that means that would work. Phosphoric acid, that's a weak acid, but this doesn't have its conjugate base. Its conjugate base would be like HPO4 or H2PO4, so that doesn't work. Here I have a weak acid, which is acetic acid, and I do have a piece of that over here. Here's HC2H3O2. Here I have just C2H3O2. So this one would work as well. Okay, so we already said that if we have both pieces in our buffer, which we do, then we have a weak acid in the buffer that's going to neutralize the base, and then we have that conjugate base part that would neutralize any acid that you added. Therefore, the pH of the solution stays the same. So I guess I want to just re-clarify that. The pH of a buffer does not have to be 7. The pH of a buffer can be anything. What makes a buffer is it keeps the pH stable when I add an acid or base, because it has both parts, part acid and part base, so no matter what you add to it, it's going to neutralize it and keep the pH about the same.